Hi everyone, so this is question 7 from your chapter 12 tutorial, heat conduction and thermal expansion. So let's look at the question. The question says you have two rods, which is A and B. You have two rods, which is A and B. And these two rods have the same length and diameter and are joined in series. So if you hear the word join in series, you should be able to imagine that the rod looks something like this. So you have rod A and you have rod B, and this rod A and B should have the same length. Okay, so this will be the length of rod A and this will be the length of rod B. And they also say that they have the same diameter. If something has the same diameter, you will probably know that they have the same cross-sectional area. Okay, so let's write down the relationship. You know LA is equals to LB. And you also know A is equals to AB. Okay, A stands for cross-sectional area. Okay, so if the thermal conductivity of A is twice that of B, so they talk about thermal conductivity, which is K, A is twice of B. So it means by thermal conductivity of A is 2 times the thermal conductivity of B. Okay, so that's the idea. So what should we do now? We are asked to find the temperature, sketch the temperature distance graph for this composite rod. Composite means by it's a combination of something and something. So for this, we know that our graph should be a Tx graph. T represent temperature, X will represent distance. So the thing is, this question is really short. Honestly saying, if this is the question, you can't really draw the temperature distance graph. So why is it so? Because there's not enough information. First, you don't even know which end is hotter, which end is colder. Okay, you don't even know what is it connected to, so you don't know which end is hotter, which end is colder. That's the first issue. The second issue is they didn't tell you whether these two rods, this composite rod, whether it's insulated or not. So let me write it down, the few information that we lack. Just now I say well insulated or not. Okay, which end is cold, which end is hot, or they are in equilibrium. You can't even know. Maybe they are in room temperature, then the whole bar has the same temperature. Then the third thing that you don't know is whether they are in steady state or not. Okay, if it's not in steady state, right, technically you can't draw a temperature distance graph. So that one, for this question, right, we are forced to assume these few things. We are forced to assume they are well insulated and it's in steady state. So these two things we just forced to assume, or else we can't draw the graph properly. So the other thing which I'm not sure is which end is hot and cold. Let's just call this part hot then, or else you can't proceed, can't learn anything. So let's just take it easy and put something in. Okay, so NA is hot, NB is cold. So now I would like to talk about something which I think many of you have a problem with. Okay, so you learn that you learn about something called thermal equilibrium. Okay, you learn about thermal equilibrium. It says that if there's heat transfer happening slowly, and things will enter thermal equilibrium, And the third characteristic of something in thermal equilibrium is all objects in the system should have the same temperature. Okay. The second thing that you might know is why is it in the same temperature is because heat flow, there's no net heat flow. Okay, so this is what you learn when you talk about thermal equilibrium. Now, is there anyone that's thinking, why won't this bar slowly get colder here? Then why won't this bar slowly get hotter? Then at the end, they reach thermal equilibrium. Anyone have this kind of thought? I would really appreciate if someone had a thought. If someone know why is it not this way, that's even better. But in case someone is having this kind of problem, let me try to help you a bit. So why this side remains always hot, this side remains always cold, and this thing never really reach something called thermal equilibrium? So the reason is like this. Okay, let me bring this to the side so we have more space to talk about things. Okay, so what happened is when you're being asked those questions, right, that give you this side having 100 degrees Celsius, this side having 0 degrees Celsius, right, what's happening is they are connecting one end of the rod to a very, very big tank of water which is boiling, and they're connecting the other end of B to another very, very big tank which is filled of ice. Okay, so what happened is actually the process is the heat is being transferred from something hot to something cold. So the bar here, the two rods here, are just a medium for you to transfer heat from one side to the other side. So now you might be thinking, if I transfer heat from this boiling thing to this icy things, then why won't the 100 degrees Celsius here drop? Then why won't this 0 degrees Celsius increase? Then slowly they reach equilibrium. So the thing is, this boiling tank here, it's constantly being filled by heat. Fire! It's constantly being filled by heat. So constantly you are transferring heat energy into the system. That's why the amount of energy here remain constant, even though there's heat flowing out, but the amount of energy remains constant. Why is it remain constant? Because you lose heat through here, but you gain heat through the energy being supplied. You gain heat through fire. So you are constantly remain at 100 degrees Celsius. You don't let it go until it becomes steam, okay? You constantly let it boil at 100 degrees Celsius by controlling the amount of fire. So if the amount of energy lost here is equal to the amount of energy gained here, then the amount of energy here remains constant. So it always remains at 100 degrees Celsius. Or you can think of this big tank of boiling tank to be extremely huge. Okay, you can think of it as being extremely huge. So if something is extremely huge, a little bit of heat transfer won't, it's like you have 100,000 million joule, let's say, okay, this is exaggeration, but 100,000 million joules, then if only 5 joules lose here, slowly 1 second, 5 joule gone, it's too minute, it's very small that it won't really affect won't really affect the temperature of the hot end of the rod, because the boiling tank here remain 100 degrees Celsius even though a little bit of energy flow out, provided you have a very extremely huge boiling tank. Okay, so it's the same thing here. So why this thing remains as ice, why this one remains at 100 degrees Celsius is because probably they put it in refrigerator. Okay, let's say I'm just saying something which you might be able to understand. So it's refrigerator, so they probably set the temperature to be constantly fixing at 0 degrees Celsius. So what does it mean is, if there's heat received here, let's say there's heat gained by this portion here, let's call it gain. Okay, so heat enter into the system. So what will happen is, through the refrigerator system, the heat will go out. It's like how you keep the fridge cold, by drawing out the heat to the outer environment. So you lose heat using the refrigerator system. So if the gain heat and the lose heat is about the same, then the net energy, the amount of energy here, remain constant. Okay, you get the idea? Or another way of thinking about it is, this ice tank here is extremely huge tank of ice. So a little bit of energy being transferred into a huge tank of ice won't really cause a significant change to the temperature. Okay, so that's what's happening when you're talking about all those fixed 100 degrees Celsius at one end, fix another end at 0 degrees Celsius. You are fixing the temperature by connecting it to something that we call heat reservoir. Okay, so actually what's here is, this is actually, if you learn thermodynamics, this is called the hot reservoir. This is called the cold reservoir. I'm not sure, but it's cold reservoir, but I can't remember whether it's called hot and cold reservoir. Okay, so reservoir, it's an idea that you have plenty of energy inside, or plenty, it's a very big thing. So it's plenty of energy, so a little bit of change of the energy won't cause much change to the temperature. Okay, that's a rough idea of reservoir. So I think that's good enough to explain the situation. Okay, so next time, if you're thinking why won't it enter equilibrium, this is why it's not entering equilibrium, because you're constantly adding heat to the boiling side, you're constantly losing heat from a system using the refrigerator system. Okay, so that's the idea behind it. I hope you gained something just now. Okay, so if the thermal conductivity of A is twice that of B, sketch the temperature distance graph. What should I do? I assume it's steady state, like I said just now. If I assume it to be steady state, then dq dt of A is equals to dq dt of B. So what happens after that is, we can sub in our formula, negative Ka AA delta TA over LA. And this one will be negative KB AB delta TB over LB. So now we can cross out a few things. We know the length are the same for LA, LB the same, then AA and AB the same. So now we are left with this, let me, how should I do this? Okay, negative KA delta TA is equals to negative KB delta TB. Okay, so now we can substitute in this thing up here. Sorry, it's a bit messy. Ka is equals to 2 kb. So what will happen is, Ka equals to 2 kb, bring in 2 kb delta Ta equals to negative kb delta Tb. So what to do now? KB is the same, negative sign is the same. So now we end up with 2 delta TA is equals to delta TB. So this is something very important here that we find out. So we find out that the difference in temperature, let's bring this, let's draw back this rod here, or else there's nothing to visualize. Okay, then we have our center, and you have rod A and rod B. So what does this mean is, if you take this as TA, and you take this as T joint, then you take this as TB, then this difference here is smaller, whereas this difference here is twice the amount of difference. Okay, so the difference between TB and TJ is twice compared to the difference between TJ and TA. Okay, so what does this mean is, if you're drawing something, let's say this is the temperature distance graph, and this is the length of A, then continue with the length of B plus length of A. So what will happen here is, you know, from A to J the change in temperature is smaller. But later, and from here to here, the change in temperature should be twice the amount. So roughly, imagine it to be something like this. So we know the line should be straight because you assume there's no heat loss, you assume it's well insulated, and we treat A as the hot end. So this one we call it temperature at A, this one we call it temperature at joint, so we call it temperature at B. So now the method that we need to do is we need to connect the graph. Connect in straight line because you assume there's no heat loss. So it must be straight line. So this one is less steep. So this one is more steep. Okay, so that's the idea of how to draw a temperature distance graph. So what will happen if it's a not so well insulated rod? It means by there will be heat loss. So if there's heat loss, right, then the graph should probably look something like this. Okay, the graph should probably look something like this because this difference is temperature here. This difference in temperature that you see here is due to heat loss. Loss of heat, and therefore temperature will get smaller. So that's the idea if something is having non-insulated rod. Okay, sorry for my language today. Okay, so that's all for question 7. I hope you learned something about steady state, you learned something about thermal equilibrium, you learned something about insulation, insulated, perfectly insulated. Okay, that's all. Thank you very much.